Welcome back to Aerospace Engineering. Today what we're going to work on is we're going to work on constructing an airfoil from a set of data points. And we'll talk just a little bit about where those data points come and how I've arranged those for you. The instructions you'll find in the module, and this is the front page of the module. These exact same instructions are probably better used and more friendly for you if you go ahead and click and download the activity itself and open it up as a Word file. So I'll give you a moment to go ahead and do that. You're also going to want to download and open the airfoil test samples Excel file. So by the magic of the internet, I've opened mine instantaneously, and you'll see that activity 1.2.7 airfoil construction is open. And as we read through this, what this does is walks you through downloading a file of points to make a wing in a 3D printer that we're going to go ahead and fly in the wind tunnel. So let's take a real quick look at this process. What you'll see here is a download of the airfoil test samples, and there's two tabs. One is for foil sim and the other is for the experimental profile. The foil sim are the numbers that I gave you as individuals to load into the foil simulator. The foil simulator is pretty limited. It really just does a symmetrical airfoil, and I'd like you to see a few other airfoils in the wind tunnel. That's why I've come up with some experimental profiles. Now I've got 17 here in this current rendition, and you're going to see that as you go across the column, there's the name for the wing, and then if it's got a NACA number, which we'll talk about in class a little bit later on in the course, I put the NACA number there. We also describe it geometrically by the maximum thickness given as a percent of the chord length, the location where that max thickness occurs, again as a percentage of chord length measured from the front edge of the wing, and then the maximum camber. Again, this asymmetry is as a percentage of chord length, and the location of that from the leading edge, again, is percentage of chord length. The end crit number, don't worry about that. That's really for me when I'm designing these and building these. And what I've done is I've chose Reynolds numbers of 50,000 so that they're relatively low airflow wings, and they should fly at that airspeed that we're going to get in our wind tunnel. Notice in column I here, you see this max CL/CD. That's coefficient of lift divided by coefficient of drag. A higher number here means essentially a more efficient wing at this particular Reynolds number. So you'll see there's more efficient and less efficient wings flying here. This also tells you where that max efficiency occurs. In this instance, 6.5 degrees and a ratio of 6.2, meaning it's making 6.2 times its lift approximately compared to its drag. So these wings come from a website called Airfoil Tools, and it downloads the wing profile itself from another database, which we don't have to get too far in the weeds. But I just want to show you that if you copy this link and then you place it into a browser tab, and I'll do that off on a separate screen here and drag this screen in, you'll see that this is the CH10 wing profile. Now, what I have done is I've downloaded these plot files for you, and I've scaled them so that they fit a wing that will fit our wind tunnel. Our wind tunnel will accept about a 4-inch chord length and about a 4-inch span of a wing pretty nicely, and it'll fly fairly nicely in there with some laminar flow. If we get much longer than that, you have a hard time. If you get significantly shorter than about 3 inches, you don't get quite the lift drag curves that we would like to see. So we want to keep it somewhere around 4 inches long, and I've scaled that for you. But all that this shows you is an outline of the wing, which I've also included on the resource page, and the plots. Now, interestingly enough, I can come down here to my Details tab, and we'll do this later on, and I can select my wing details, and now I can see this coefficient of lift versus coefficient of drag plot, and you'll see where this happens, this coefficient of lift versus coefficient of drag versus AOA, and you'll see that's that peak point at 5 that I was pointing out. So this is where the numbers come from. Now this is generated using a much more sophisticated airfoil analysis program than the online NASA one. And that's kind of why we're using these wings, so we can get a little better data out of it. All right, so what we've done here is we've picked a wing, or we've been assigned one. And for example, I'm going to go ahead and do the date and Wright flyer here. Wing foil number 12. This is, oh sorry, no, it's an Eiffel. It's number 14. Eiffel 10 is the Wright flyer wing. And you'll look at it, you go, oh, that's an interesting looking little wing. Well, it's one of the first wings that ever flew, the first one that flew under powered flight. So let's go ahead and go back to our web page and pull up the tab for this. So here's my tab, and you're going to see that I'm going to scroll down here and go ahead and find my Eiffel 10. And there's the profile for it. So I've given you the text download and the profile. What I want to do is right click on this, and I want to go ahead and save that link as something. I'll put it in Westwood Engineering, my first hour wing, and I'm going to save this. Sorry, I want to click on this. And here I want to download it. So save link as. And now I'm saving my text file. And you're going to notice this text file starts out at 100. These are in millimeters. So this is my X coordinate, my Y coordinate, and then my Z coordinate. So X, Y, Z. And you'll notice I start at 100 and I pretty much finish at 100. So it'll be close to a closed body. Probably won't be perfect though. So I've downloaded that wing file, and I want to go ahead and open that up in Excel. So let me go ahead and bring up my Excel, and I'm going to go File, Open, and I'll navigate to where that wing is. And here that wing happens to be here, the Eiffel 10-IL. And I'm going to go ahead and open it. When I open it, you're going to see I've got some different limit, or I've got some different ways it's going to import the text file. And what I'm going to ask it to do is I'm going to say it's a delimited text file. So right there, delimited text file. Go ahead and click Next, and now you'll see it's tab delimited. That's how I've saved all these. And here's my data. As I scroll through, I can actually see all my data points. I just go Next, Next, and then go Finish. And what that's done is it's put my X numbers in the A column, my Y numbers in the B column, and my C column represents my Z numbers. So I can make an X, Y, Z curve. Looks pretty good. If I want to actually validate this, I can select my X and Y's and insert a scatter plot. In that scatter plot, this is kind of what my airfoil looks like. It's a little bit exaggerated, and we don't need to get super crazy about making a perfect X plot, but that looks pretty good to me. So I'm happy with those, and all of these text files have been proven out, so they should all work for you. I'll go ahead and close that window. I don't need to change it. I don't need to save it. So now I've got my text file saved. What I'm going to do is go ahead and start a new file. I've started Solidworks in the background, and I'll go ahead and give you an opportunity to pause the video and start Solidworks. Okay, hopefully you're back. Solidworks is up and running. Let's go ahead and start a file, new, and I'm going to select a new part. You may see the novice window, or you may see the advanced window. Either way, select part. If you're in the advanced, be sure you're using the Westwood Engineering template. This does a few things for you. Very first thing I want to do is get myself into the unit of measure that my XYZ plot was based upon, and that was millimeters. So I want to select MMGS as my units. So MMGS, where my cursor is flashing. Now what we're going to go ahead and do is we're going to use on the Features tab up here, we're going to import a curve. And the curve we're going to import is going to be an X, Y, Z curve. So a curve through X, Y, Z points. Select that button, and it brings you up to this window where it says, hey, what curve points do you want? You could fat finger in the points, but instead we've elected to build that on a data file already. So let's go through and go browse. And here I'm going to navigate to where my airfoil is, and I'm in first hour, And I need to go ahead and change this curves default to a text file. Now, be a little careful here. If you left that text file open in Excel and you now try and open it at SolidWorks, SolidWorks will give you an error and say, hey, the file's in use. So be careful of that. Be aware of that. I'll go ahead and select my Eiffel, foil number 14, Eiffel 10, IL, is just the part number. And I'll go ahead and open it. As soon as I open it, notice what I get over here in yellow, where my cursor's flashing. I see the profile that these points define. So there's my profile that my points define. If that profile does not appear, it means your file's corrupt and it won't work. It can't interpret it. So this tells you, hey, this is what I'm going to bring in. Simply click OK. And I've brought curve 1 into the file. I'll go ahead and pause it for now, and we'll pick it up when we start an extrusion.